Now that we know what a quad tree is, let's see how they can help us with performing a two-dimensional range search or rectangle search. So the same idea is going to be what we just saw, where if a certain part of the tree has no possible answers for us, we're going to ignore it. And so to get a sense of really how that works, let's just walk through an example. So the goal, to make sure it's very clear, is to find all of the points between A, B, C, D, and E that are inside the green box. Now that seems like a silly problem. Like you and I can immediately tell that the answer is B, and all the other points are not in there. However, from the computer's point of view, what the monks in the cave are manipulating is they have a quad tree, where here's the root, it is A, and so they have to start the search at A. That's where they begin, right? They can't just immediately look over there and see B. They're going to start at A. So we start at the root, and we ask ourselves, is A inside the green box, the green rectangle? Okay. No. Well, then we ask ourselves, since A is not, which subspaces might have good points? Well, there are 4 subspaces. There are all the points to the northwest, all the points to the southwest, all the points to the southeast, and all the points to the northeast of A. And of those, only the northeast could possibly have any good points, where a good point is a point that is inside the rectangle. Why? Well, this top left quadrant, it has no points in common with the rectangle, so we know that there's no possible way that anything over here could be in the rectangle. Now again, you and I can tell there's actually nothing here anyway, but again, from the computer's perspective, this means we don't even need to look at this null link to realize that it doesn't have any points. We can just immediately throw it out. And that's the glory of pruning. Okay? So we continue on. And we move to our one remaining child, which is B. So we look at B and we say, is B in the box? Is it in the green rectangle? Yes, it is. So let's add it to the results. And then we ask ourselves, which of the subspaces might have good points? So this is a great place to pause the video if you want and figure out what are B's subspaces, first of all. And 2, which of those subspaces are actually useful, could actually contain a point that is inside the green rectangle. So try that out. I think this stuff's pretty beautiful. I like the geometry a lot. So it's an exercise worth doing. So in this case, B's 4 subspaces that it owns are this top left, top right, bottom left, and bottom right subspace. Now in this case, all 4 contain some space in common with the rectangle, so we need to explore all of them. Now one quick note is that B's subspace does not include all this stuff over here. And that's because B is it's a northeast child of A. So the space that it owns won't include anything at all outside of the northeast corner of A's universe, right? It's a recursive data structure that shrinks the space as you go deeper and deeper and deeper into this quad tree. Okay, so be aware that B's spaces are just what we see here. All right, so now we need to consider all 4 of B's subspaces, so let's do it. So we'll start with the northwest corner. Well, it turns out that one's just null. Okay, so since the node is null, we just return. Next we consider, let's say, the northeast link. Well, that one you see is also null, so we don't have anything to do, we just return. Now we look at the southeast corner. Well, that one's also null, so we just return. And then finally we get to the southwest corner, which is a point. Okay? So at this point we say, is C in the rectangle? No, look, it's not, right? This is some coordinate, here's the rectangle. You do just some if statement of some kind, and you say no. So now we need to consider C's subspaces. So again, maybe pause the video, figure out first what are C's subspaces, and 2, which ones are useful. So in this case, C's subspaces are as shown. So it's got a top left, a top right, a bottom left, and a bottom right. Okay. And here, the only one that could possibly contain any points from the rectangle is the northeast corner, right? Because, well, you look here. This is it has an intersection with the green box. The other 3 do not. And so we can prune the other spaces, or the others entirely. Okay. So at this point, we do not need to consider the other 3 subspaces, so we'll head straight to this northeast subspace. Well, this northeast subspace, it turns out, is just null, so at this point, we're done. And so what we observe is we are able to prune off 1, 2, 3, 4, 5, 6 links directly, but indirectly, we also pruned off everything that was below E, everything that was below D, and in a larger problem, it could be an enormous savings. All right, Oops. So that's the basic idea behind what QuadTrees do for us. It's a really beautiful idea. It's a different way of partitioning space. And really the thing I want you to hopefully sink in very deeply, it's just a different way of partitioning space. In this case, the partitioning is done where each subspace is owned by somebody, right? So D owns these spaces. Where in our other approach, it was just like space, there were different regions that were independent of actual objects. Okay? So it's a pretty deep idea. And if you go into computational geometry or that kind of area of study, you'll go way deeper into this stuff. But yeah, just want to give you a little taste of how QuadTrees work. Now, I'm not satisfied just there, because I want to step up our game, and I want to go even beyond two-dimensional data, and that'll be the topic of our next video, where we talk about 3D and beyond.